Alright everyone, let's go ahead and solve a question from the compressed liquid water table, just for us to get going, okay? Now I have a rigid tank still, and now I have fairly large 1 ton or 1000 kilograms of water. And now pressure is pretty high, you can see 5 megapascal and 40 degrees C. And I'm asking you, what is the volume of the tank? This time I didn't give you the volume of the tank. And I'm using two approaches. The approach one is the appropriate approach, by using the compressed liquid water tables. And those tables are A7 for the SI, A7E for the British gravitational, okay? In part B, I'm taking a shortcut and I'm doing, why don't I go ahead and say that liquids are incompressible? How much off am I going to be at the end of the day? Is my efforts worth it by using more accurate technique, okay? So I will discuss that. Again, as always, please try to do it on your own first, okay? Don't watch the whole video. Okay, let me start going. So the part A is kind of clear. It says that go find the compressed liquid water table. And that's called A7. Do you remember that? A7. And this is SI, right? In terms of the units, it's given to me in SI. So I will be using that table. And if I look at that particular table, I have a 5 megapascal and 40. These two basically state is not defined because of the state postulate. Two independent properties are given to me. So if I look at it, well, the specific volume is 0.00157, very small, right? Makes sense. This is a liquid, the density is fairly large, okay? And it's asking me the volume of the tank. So if I go ahead and convert this to the volume, what will happen is the specific volume was defined as volume per unit mass. So then if I go and do this, I will see the volume will be equal to specific volume times the mass. And this is 0.00157 meter cube per kilogram times 1000 kilograms. And if I do it, 1, 2, 3, yeah, 1.0057 meter cube is what I'm going to get. So this is the answer to the question, okay? Appropriate way. Okay, let me tell you before I go to the B. Let's say that this pressure is given as 1 megapascal, not 5 megapascals, okay? So unfortunately, table A7 starts at 5. I don't have a table that shows me what is the properties at 1 megapascal, okay? So in those kind of cases, I am forced to use the B approach. In here, I have an option because I gave you the pressure on purpose as fairly high, so I can, compare, contrast the two tables and see how much of a mistake I'm doing. Let's just go and do it and see compare to each other. So the part B is, as I mentioned, I'm going to take the temperature as 40 degrees C, and if I actually go ahead and explain you in a PV diagram, I think it will make a little bit more sense. At least that's my hope. Something like this, something like that, something like this, okay? So this is at, basically, I'm saying that this is at 40 degrees C, okay? So in order to obtain the properties at 40 degrees C, I need to go to the table A4, right? So I look at table A4, and I look at the basically this number, okay? So you see this, there's a slope to it over here, okay? And you will see that the reality should be a little lower than this number, right? Because I'm going up like that, because see, this is 1.00, well, here, 0.00157, right? So then it means I'm somewhere here, right? Because the pressure is higher. If I go down here, you will see that I'm going to get a slightly larger than this value, but how much larger, okay? So to do that, I go to A4 and I read the saturated liquid specific volume information. So you can see, so far so good, right? Exactly the same. I'm doing a suspense here, you can see. And then 8, okay? So you can see this is 57, this is 8 at the end, 80 rather, at the end, okay? So, okay, so this is meter cube per kilogram. And if I go ahead and find the volume, that will be mass times specific volume that I'm giving you, 118 meter cube per kilogram times 1000 kilograms, and I will get myself 1.008 meter cube, okay? So you can see this, you can see that, okay? And actually, if I want, I can do like a error analysis. This is the accurate one. So I can do this minus that divided by that times 100, right? Percentage. And I did it actually, just to illustrate to you. My error is 2.3%, so that's nothing. Okay. In reality, you can see that this particular case, we don't have much of an issue with this kind of an assumption. But one thing to note is I kept the temperature as constant, right? If I keep increasing the pressure, my error is going to keep increase and increase. Just want to highlight, okay? In the case that my pressure was, let's say, 50 megapascal, I will have more error in my analysis. It's not going to be a huge amount, maybe it's 4% or something, but the error will increase, okay? Just want you to be aware of that. All right, that's going to do it for this segment. It's pretty short, but it's important to go over these things too, okay? Have a good day.